Well, welcome to Wave Club, everybody, on this hot July 1st summer afternoon. My name is Josh Jacobs, and I'm one of the organizers of Wave Club, along with Bard Ehrmantraut, Uma Mohan, and Irfan Zabeh. And Wave Club, as you probably know, is a monthly online meeting group that we have to talk about this interesting topic of traveling waves in the brain. Um, and I'm really happy everyone's here. Our speaker today is Roberto Budzinski from the University of Lethbridge. Roberto is going to talk about a new mathematical framework predicts specific traveling waves from network structure and systems of nonlinear oscillators. It's a rather computational talk today. And that is makes sense given Roberto's background as a physicist originally. Um, he did a PhD in physics, studying synchronization properties, malleability of synchronization, and nonlinear states in neural networks. And he's now doing work developing mathematical and computational frameworks to understand how biological and artificial neural networks organize activity across space and time. Um, and Roberto, we're just really happy to have you here today. Uh,
Yeah,
and
thanks so much.
Yeah, thanks. As a reminder, we archive all of our Wave Club recordings on YouTube, and it's a really nice resource for people who want to go back and uh, learn things that they missed or get refreshers. You can go to YouTube and type in at Wave Club Seminar to find all of our previous seminars. And if you want to follow more Wave Club seminars, these happen about every month. You can come to our Blue Sky page here. I think we also post them on Twitter as well, or X, whatever Elon calls it these days. The plan for Wave Club, as in most months, is to have about a 40 or 45-minute presentation by Roberto, with about 15 or 20 minutes of questions at the end. Um, it's perfectly Roberto will be running the show, but it's usually perfectly fine to have like small technical clarification questions in the middle of the talk, and it's probably better to have bigger questions at the end. If you want to type your questions into the chat at the end, we can bring you on stage and have a conversation between you and the speaker and other folks here. And just going forward, we are always looking for different speakers for Wave Club, and self-nominations are very welcome. So please reach out to me or Irfan or Uma or Bard if you are interested in speaking at Wave Club, or if you have particular people that might be relevant that you think would be a good presenter. The main theme of Wave Club is all about traveling waves, both from a computational and experimental perspective, either one in any animal species. And both more mathematical as well as experimental approaches are really encouraged. So we would be great for you to come join us with different kind of diverse presentations. Um, we are skipping the August Wave Club presentation due to the summer, and our next speaker is going to be in September, where Alex Oppitz is going to talk. He's a professor at the University of Minnesota, so you can keep an eye out for that, and please keep an eye on our email list if you want. And I think that's it for my little introduction here. And I'm going to stop my screen sharing and turn this over to our speaker, Roberto. Um, Uma and Irfan, did I miss anything important before Roberto takes over?
All good.
Okay. All right, good. Well, thank you everybody for coming. Uma, Irfan, thank you for helping organize this. Roberto, why don't you share your screen? We're delighted to have you here today. Thanks a lot.
Yeah, thanks so much. Let's just make sure that you guys can see my screen. Oh, good, right? And you can hear me well as
Yeah,
well, right?
it looks great. Yep, thanks a lot.
Awesome. Yeah, thanks so much for the invitation and for having me here today. And happy Canada Day for everybody. Today's Canada Day, so happy Canada Day. And so just before I start my presentation, I just want to note that I love Wave Club and I've been attending like lots of the talks here. And I think my talk will be more on the mathematical and the theory side. And I will and so, if you guys have, I will try to keep this more like, try like to explain to you the ideas and leave the mathematical details for later. But if you have like any question that you want to ask or any clarification, feel free to do so during the presentation. If the question is too big, and then we can discuss later. And so what I will show you today is kind of like an overview of the mathematical framework that we have been developing in the past years. And this mathematical framework, it allows us to answer two main questions. So the first question is that it allows us to directly show how the network structure is shaping the resulting dynamics in leading to traveling waves, for example. And the second question is that it allows us to train or design neural networks to perform computations using these organized spatial temporal patterns. So before I start, I just want to mention that what I will show you here today is actually a joint effort of many collaborators. And particularly, I want to emphasize the collaboration with Lyle Miller, my former postdoc supervisor, and Alex Bush, a PhD student in Lyle's lab that is now moving to Princeton on a CV Star fellowship soon. And this collaboration is actually happening under this joint effort of the Fields Lab for Network Computation, where our goal is to develop mathematical and theoretical approaches to understand neural computations in both biological and artificial systems. And to start my presentation, I want to give you a little bit more of context. And I know that probably most of you have already seen this example here. And I know this has been already shown in the Wave Club in different talks. But I think this is a beautiful example that shows this surprising amount of spatial temporal organization in the human brain. So this data set is given by intracranial recordings from human subjects doing electrophysiological mapping procedure for treatment of epilepsy. And this example shows the case of sleep spindles, which is these narrowband oscillations that happen during sleep, and they are related to memory consolidation. And here we have a spatially distributed set of electrodes where we are plotting the individual ECOG electrodes directly on the cortical surface, and we are showing the normalized potential here in color code. So this is a video, and when I play this video, you will see these colors changing, representing this spatial temporal organization. This red dot is representing the trace here in black, and the other channels are represented in gray. So this is a typical example of the spatial temporal pattern here. So here we are seeing 5 cycles of this spindle oscillation. And we can clearly see that the spatial temporal pattern in this case is organized into a rotating wave across cortex now, going in this direction here. And what is quite interesting about this result is that the distribution of speeds of these waves, they consistently peak between 2 and 5 meters per second, which fall in the range of conduction speed for these long-range fibers that are connecting these different brain areas. So this is interesting because this is suggesting a possible network mechanism for these waves. Specifically, the time delays it takes for these spikes to travel down these long-range axons may be shaping the spatial temporal pattern at this macro scale in the human brain. And I want to show you a second example, and I know that this has also been shown here before, but it is also a very interesting example because it shows these traveling waves and this spatial temporal organization also at a different scale. So before we saw this organization at this macro scale, and now we have these are neural recordings. This will also be a video, and these are neural recordings from the region V5 or MT in the visual cortex of a marmoset monkey. And the colors here will change when I play the video, and this is representing the LFP. So when I play the video, you will see this changing over space and time. And this is in fact a spontaneous traveling wave that is sweeping this entire cortical region. And what is interesting here is that the authors show that these spontaneous waves, they're actually modulating excitability of local networks. And with that, they are gating perception in awake behaving animals. And what is cool about this is that a mathematical modeling work that followed this result has shown that cortical networks with distance-dependent recurrent connectivities and delays can produce these wave patterns. And again, this is indicating this role of the network structure on the emergence of these traveling waves. And obviously, this is just like, I don't think I need to convince this audience too much about the importance and that traveling waves are interesting in neuroscience. But I just want to show you these 2 examples at first, just to show that first, like these waves exist in these different scales. But also the role of this underlying structure. So the connectivity and the delays might be playing a role in the emergence of these traveling waves at these different scales. And the last thing that I want to mention in this brief introduction is that beyond neuroscience and biological brains, traveling waves have been also observed in artificial neural networks. So there are many beautiful works out there showing the emergence of traveling waves in recurrent neural networks after training. I know that Andy Keller just joined us. He has a great paper showing these traveling waves in these recurrent neural networks. And the idea is that these waves might be helping with computation that these networks are performing. So now, with these two quick points in my introduction, I just want to say that we have the evidence for the existence of these traveling waves in both biological systems at different scales and also in these artificial neural networks as well. And what this is giving us is kind of like this evidence for this correlation that they might be important for computation. But the question that we are interested in is that the exact computational role of these waves and more broadly, organized spatial temporal patterns in both biological and artificial neural networks, it remains still unclear. So what I will show you today for the next, 35 minutes or so, it's a summary of our recent efforts to address this problem. And what I will show in this presentation is the mathematical framework that we developed in the past years that might help us to understand how these complex patterns are emerging and how they are supporting computations in both biological and artificial systems. So just to formalize and finish my introduction, this is actually the main question that we have in our research program. And actually, this question is kind of like divided into two parts. So first, the first part of this question is, how does the network structure, here including delays and connectivity, how this is shaping the resulting dynamics and leading, for example, to traveling waves or more broadly, different organized spatial temporal patterns? And the second part of this question is, how are these organized spatial temporal dynamics supporting computation? And so, as I said, we have been developing, we have been treating this question from a mathematical and theoretical perspective. And what I will show you here today is this mathematical framework that we developed that might allows us to create a path to answer this. And by these two questions. And by doing so, we have like these direct applications, for example, in computational neuroscience, where we can study how brain connectivity is shaping neurodynamics. And specifically, we are interested here at the level of individual cases. And also we have applications in AI, for example, where we can study how specific weights of a trained neural network or design neural network, how they're supporting the emergence of organized spatial temporal patterns and how this is supporting specific computations. So my talk has roughly these three main parts. So first, I will give you an overview of this mathematical framework. Then I will show you how we can use this to predict the emergence of traveling waves in terms of individual connectivity matrix and delays. And then in the last part of my talk, I will show you how we can use this framework to kind of like create like a theory of spatial temporal computation, how networks can use spatial temporal dynamics to perform computation. And before I start this first part, I want to note that, as I said in the beginning, I think my talk will be more on the theory side, the mathematical side. And this first part is the mathy one. And my goal here is to give you like the high level description and to explain like, the main idea behind this framework. And for those that are interested in the mathematical details behind this framework, I'm happy to chat later in the end of the presentation or to point out the papers where we actually discuss and prove all the mathematical things behind it. But here I will focus on the main level description. And to start introducing this idea, I want to mention that we are dealing here with networks of coupled oscillators. And so this is a very simplified schematic representation of the network where each dot here is representing one node or one oscillator, and the lines here are representing the connections between them. And I want to mention that while this is a very simple example, just for us to start building up the intuition, I want to note that our framework is actually general to any graph. And I will show you, for example, later applications on in the human connectome, for example. But to build up the intuition here, I want to also note that there are different ways to model oscillators, and here one of the main models that we are interested in ways of thinking about these oscillators is using the Kuramoto model. So the Kuramoto model is this canonical system in physics to study synchronization and has also been used in neuroscience. So I think it was a couple of months ago, we had a great presentation by Dominique where he showed like how they can use this Kuramoto model in this coupled oscillators to study large scale brain dynamics in the human brain. But just very briefly to describe the model here, the equations, it's not a complicated model in the end of the day, and that's why it's such an important model because it's we can do a lot here. We can study this in more details. And the idea is that theta here is the state of each oscillator or each node, in this case, the phase of this oscillator. Omega is the natural frequency of oscillation. We have a parameter here that is this epsilon that is like a scaling parameter that we can turn, like make the connection stronger or weaker. It's kind of like a control parameter that we can change. And then the interesting part starts here, that this is where this sum starts. That's where the coupling starts. So we have a sum over all nodes in the network, and this sum will have like this term that is this matrix element, and this matrix A is the adjacency matrix. So this is the connectivity matrix. It's telling us who is connected to whom and what is the weight in that connection. And then here we have the nonlinear coupling, oscillator J and oscillator I. And the last important piece of our framework here is that we are considering time delays. As I mentioned before, we have this evidence that time delays may be shaping the neurodynamics and overall organizing traveling waves and spatiotemporal patterns. So we have heterogeneous time delays in our framework here in the interactions between nodes J and I. And the idea is that, so this is composing the model, all the elements that are important there. And the idea is when I take like all these parameters, natural frequency, coupling, and most importantly here, when I say network structure, what I mean here is the connectivity of the network and the delays in the network. So this is defining my network structure. And when I put these oscillators in this network structure, the interactions because of these interactions, we will see the emergence of these organized spatiotemporal patterns. So this is just a quick video with a quick example. So here, each black dot is representing one oscillator. The oscillations will be going up and down in this case. And I'm not representing the connections just for the sake of visualization here. And in the beginning is disorganized, but because of these interactions, we can see this emergent behavior. So some oscillators are synchronizing, other oscillators are falling out of sync. We can have like waves appearing here and more complicated patterns. And the question is, or the first part of the question that I want to address in this talk is, how does the network structure lead to specific dynamics? And again, by network structure, I mean the connectivity and the delays. And this is actually not a new question. This is an old question. And there are already like great work in the literature trying to address this. For example, Bard, one of the organizers here of the Wave Club, has amazing work here that has been always inspirational to us. So this is a problem that has been explored from different perspectives. What I will show you here today is the approach that we developed to deal with this. And the main focus or the thing that I want to focus here that is our main interest is that we want to develop a mathematical approach that is valid for individual networks. So say I have one specific connectivity, one specific set of delays, how is that leading to specific patterns of spatiotemporal dynamics? And this is usually a complicated question to ask and to answer from a mathematical perspective, because these are nonlinear systems, the interactions are nonlinear. And because of that, it is kind of hard to see exactly how that matrix, the connectivity matrix and the delay matrix, how they are combining at the individual level to generate specific dynamics. So in the past years, we actually developed a new mathematical framework to try to address this problem. So as I said, I will give you the overview here and happy to discuss the details later. But in a nutshell, essentially, we found a nonlinear system of complex valued oscillators that are kind of like similar to the Kuramoto model, and they have an exact mathematical solution. So because they are complex valued oscillators, one of the things that we are doing here, we are actually changing the underlying algebra to go to the complex numbers. But by doing so, we actually gain something. And this is the ability to re-express that set of nonlinear differential equations that I just showed you before in the previous slide in the Kuramoto model. So now we are able to re-express that specific set of nonlinear differential equations as a combination of operators and special functions. And these in turns open a new possibility to link the eigenvalues and eigenvectors, the spectrum of the network structure, and again, meaning connectivity and delays, with the resulting dynamics. So let me explain you a little bit more how this works. So essentially, we have now a complex valued approach, or an operator approach that we call. And the idea is that instead of solving the nonlinear differential equations with numerical simulations and all those things, we are actually propagating the solution that we found for this nonlinear system of complex valued oscillators. We are propagating the solution in windows of time. And to do so, we actually found that we can use a matrix exponential operator applied at this state, this complex valued state that is represented in the oscillators. And the key thing here is that in the derivation of the model, we actually found that we have a composite matrix that is aggregating all the information that is relevant in my Kuramoto system or in these oscillator networks. So the coupling strength, the delays, and the connectivity is all together in one composite matrix. And there is this matrix exponential of this composite matrix that has all the information about the network structure that I can apply this operator on my state of this complex valued oscillators, and this will generate the evolution of my system. And then on top of that, we also found that we need this nonlinear operator that is essentially bringing this complex valued state back to the unit circle. So is normalize the state vector in the complex plane. So essentially, this is giving us now a description of these nonlinear oscillator networks in terms of operators. So I have this linear operator and this nonlinear operator. As I said, I know that I'm not showing any of the mathematical details. I just want to give you the main ideas. All the details are in these papers, and we can also discuss later if you're interested. But the thing, and so with this operator description, with these two operators applied in these specific ways, we found that there is a correspondence so between this complex valued system here in X, and so the argument or the phase of this state, this vector X, is actually equivalent to the Kuramoto model, to the dynamics that we see in the Kuramoto systems. And you might ask, okay, great. So you have a new way to see the dynamics in Kuramoto oscillators. Why do I care about that? I can do numerical simulations of that set of nonlinear differential equations. That's true. The thing that we care about this, as I said, because we have this combination of operators and functions, it actually opens a new way to link the spectrum of this matrix K with the resulting dynamics. Specifically, what we can do is that we can do an eigen expansion. So we can take the eigenvalues and eigenvectors of this matrix K, which again has all the information about my network structure, and I can expand this matrix exponential in terms of these eigenvalues and eigenvectors under this nonlinear operator. So essentially, this is already pointed out, like this is the first step that is pointed out during the derivation that we found. It's because this matrix has all the information about the network structure. This is the direct link between the eigenvalues and eigenvectors. When I change my connectivity and the delays, I will change my eigenvalues and eigenvectors. And this is already the first step in that direction to make this link, to link the network structure with the resulting dynamics. And specifically, what we found is that it's not just the eigenvectors, but there is a nonlinear function that is applied on the eigenvectors. And all of this we found during the derivations, all the proofs are here, right? But the important thing is that we found that it's not just the eigenvectors, but it's the phase or the argument of these eigenvectors that are actually the building blocks of these dynamics in these nonlinear oscillator networks. So to give you a little bit more intuition what that means, so say, like this is a very simplified network. I promise you we will get to the brain network in just a bit. But the idea here is that each oscillator is connected to neighbors on the right, neighbors on the left. And because of these interactions, we will see the emergence of these organized patterns, as I showed you before, right? So this we can get from the numerical simulations of the differential equations and stuff. But as I said, with this new framework that we developed, we actually found this link between this spectrum of this composite matrix through this nonlinear function. So the phase or the argument of the eigenvectors become the building blocks of the dynamics that we will see. And specifically, the thing that is very interesting here, at least I find interesting, I know I'm biased, but I hope you'll find interesting too, is that we can actually see the spatiotemporal impact of these eigenvectors directly on the dynamics. So, what I told you so far is that we have this composite matrix and we analyze the phase or argument of the eigenvectors, and they are the building blocks. Now let me show you how exactly or what I exactly mean by that. So we found that if we take the phase or argument of these eigenvectors, and then we plot on the physical space where the network is defined, this will literally tells us the spatiotemporal impact of these eigenvectors and the dynamics. So just to show you some examples, these are just like a few examples of the eigenvectors of this network here. So we are taking, the composite matrix K, calculating eigenvalues and eigenvectors, taking the eigenvectors, phase or argument of these eigenvectors, and now we are plotting this exactly on the range where the network is defined. And what this tells us is that, so this eigenvector here, for example, this has a physical meaning. This eigenvector is representing phase synchronization. All nodes have the same phase. So we know that the spatiotemporal impact of this eigenvector in the dynamics is leading to synchronization. But other eigenvectors also exist. For example, here we have this phase offset. So it's increasing here from light blue to green, going to red, and then wrapping around like minus pi and pi. So what this the physical interpretation of this eigenvector is that this represents a traveling wave around this ring with one cycle around the ring. This other eigenvector also represents a traveling wave around the ring, but now with two cycles. And we will have different eigenvectors with different spatial frequencies, different directions. And now through our approach, we can literally see the spatial temporal impact of these eigenvectors on the dynamics. So just to give you a couple of examples here, and here I have two videos. So here on the left is the network dynamics, and here the color is representing the phase of each oscillator, again, on the ring. So black means minus pi, and white means pi, the phase of the oscillators. So in the beginning is disorganized. When I play the video, you'll see the dynamics changing. And here on the right, this is the contribution of this dynamics onto each of the eigenvectors that I have in my system. So in this case, the network has 100 nodes, and I have 100 eigenvectors in my system. So I'm calculating essentially the eigenmodes contribution in this case. So when the dynamics is disorganized, asynchronous, everybody has similar contribution. But we can see that as time changes, this first eigenvector becomes more important, and this is exactly when the network is transitioning to synchrony. And when we look at the argument of this eigenvector on the physical space where the network is defined, this is literally representing these dynamics. So I can show you another example. In this case, it will be a traveling wave. So again, the same idea as before, the network starts disorganized, and here is a different eigenmode that is becoming important. In this case, is the eigenvector number 3. And we here, as this increases, we can clearly see a wave starting to appear, a traveling wave. And then when we look at the argument of this eigenvector, it literally represents this spatiotemporal dynamics. So now we can, obviously, those are two simplified cases. And now we can go to a little bit more complicated patterns. So again, the same idea as before, but now the network is in a different configuration. So we will see the emergence of a different pattern. So we'll see the eigenmodes contribution changing. This first one is trying to dominate like it did it before, but kind of like the other eigenmodes are pulling it down. And we can see on the dynamics here that part of the network is now synchronizing. It's not the entire network. It's just part is synchronizing while the other part remains asynchronous. And the first mode is not escaping anymore. But now, instead of having only one eigenmode being important, we actually have a combination. It's a constellation of our eigenmodes. And by the way, this is one simulation, but we can do that in many simulations, and we still have the same set of eigenmodes. And the key thing here is that we actually have a physical interpretation what this set of eigenmodes actually mean. Um, so here in this case, is essentially like we have the synchronizing mode and also these low spatial frequency waves in both directions around the ring. So it's like writing a standing wave in physics, right? Like these waves are going opposite directions and kind of like creating this synchronized cluster here. So for example, we did like some controls there. If we kill some of these modes, so say that we only have waves going in one direction, and then we don't have like this synchronized cluster. So now we have like this kind of like unified way through this framework that I introduced before. And this is literally telling us from that composite matrix, that matrix K that has all the information about the network structure, we can calculate these eigenvectors and then use our framework to interpret that. So the phase of these eigenvectors, the argument of these eigenvectors, plotted in this physical space where the network is defined, is giving us the spatial temporal impact of this set. And it can be, for example, in the simple case, a synchronization or a simple wave, it's one single mode. But when we have these more complicated patterns, we actually have a constellation. And just to finish this part here, I want to mention, so for example, we could use, for example, I don't know, like some dimensionality reduction technique like PCA. We take all these dynamics, we do PCA on that, and we'll probably will be able to separate synchronization from waves and stuff using the principal components. We know that PCA is linear and there are some problems with that, but we probably will be able to separate. But then what can we learn from that, from the sense of how is the underlying structure actually leading to that dynamics. From like this dimensionality reduction, sometimes we can interpret these dimensions, but sometimes we can't. What I'm showing you here is this nonlinear approach that is giving us these eigenvectors, these eigenmodes directly from the network structure. And with this, we have this first unified geometry, but also this physical interpretation, what these directions, what these eigenvectors actually mean in terms of spatial temporal organization. And then in turn, when I will switch now to the second part, this will actually allows us to have mathematical predictions of what will happen in the system. So, like now using this approach, I will show you how we can go from the connectivity and the delays in a single network to predict the waves that the system will have. And again, this is, I promise you, like this, we will get to the brain network. Let's just like use like this simplified network just like one more time. So we really like finish like building up the intuition. So again, it's the same network as before. Each oscillator is connected to neighbors on the right, neighbors on the left. And this is actually the connectivity matrix, the adjacency matrix. Black because it's connected, white when it's not connected. So we have, the connections in both directions. That's why we have this band on both sides. But as I said in the beginning, we are interested in that we want to explore the effects of delays in the system. So here I will also consider distance-dependent delays. So the nodes are connected here, and the further away they are, the longer is the delay. The closer they are, the shorter is the delay, and this is represented in this color code. So blue is longer, green is closer or shorter in this case, and white means no connection, no delays. So the question that I want to answer using my approach now is, okay, I have this specific network with this connectivity and these delays. How is the connectivity and the delays combining to generate specific spatial temporal patterns? Can I predict that just by looking at the connectivities and the delays? The answer is yes, and then I will show you how we can actually do this with our approach. So to do so, I will do exactly these steps that I showed you before. I have my operator description. With that, I can have my composite matrix, that matrix K, that has information about the network structure. And then I calculate the eigenvalues and eigenvectors of that matrix. And just to show you, so without delays, these are the eigenvalues of my matrix K. And the largest eigenvalue here in real part is actually associated with the eigenvector whose phase, when we plot in the physical space, represents synchronization. So the way to interpret this is that without delays, the network will actually transition to synchronization. And this is a well-known result in physics. For that specific network, without delays, the network will transition to synchronization. So this is more like a sanity check to make sure that our approach is able to explain like these well-known cases. But what is very, very interesting is that now we can use exactly the same machinery and go to the case with delays and distance-dependent delays, the matrix that I showed you before. And what we were able to show is that the delays are actually not changing the eigenvectors. So the eigenmodes are exactly the same, but the delays are changing the eigenvalues in this case. Specifically, they are rotating the eigenvalues in the complex plane in such way that the mode that is associated with synchrony is no longer the dominant. So this, we already have one first prediction here. With this distance-dependent delays, the network will not synchronize. And that's the case, will not show phase synchronization. And the second prediction that we have is that now we can look at the largest eigenvalue in real part is no longer the one associated with synchrony, but it's an eigenvalue associated with this mode that represents a specific wave with a specific spatial frequency. So what this means now is that we can go from this connectivity matrix and the delay matrix here, we can go directly to a mathematical prediction. What is the spatial temporal pattern that will result from this combination here? So by calculating that matrix K, eigenvalues and eigenvectors, I take the largest one, argument of the eigenvector, and then I plot that on the physical space where the network is defined. And this becomes a mathematical prediction. What is the dynamics that will emerge in terms of this connectivity and delays? And then when we run the simulation, we can actually see that this agrees with the prediction that we have here. And the thing is that if we change the connectivity here, say that you increase the number of connectivity or you change the delays, this prediction will change, like the eigenvalues will change, different waves will appear, and now we are able to tell, even before running any simulations, just by looking at the combination of connectivity and delays, what is the type of wave that will emerge in the system. And now finally we can get to the brain network. And that's one of the main points here, is that because our approach remains finite, we can actually go straight to empirical data as well. So for example, consider the long range fibers from the Human Connectome Project. And so from here, we can have the weights connecting different brain areas. And this is now my adjacency matrix. So it's the same idea as before. Before it was very simple, binary. Here we have different shades of gray, and this is essentially representing different weights in this connection. And from this experimental data, I can also have the length of the fibers. So I can estimate my distance dependent delays, and that's the matrix that I get here. And just to show you, we can focus in one hemisphere, just to show you it's much more complicated than before, the delays as well. But the idea is exactly the same. I can go from the combination of connectivity and delays, create my matrix K, get the eigenvalues and eigenvectors, get the eigenvector, phase of the eigenvector, and now I plot in the physical space where the network is defined. Is no longer the ring, is this 3D space where the brain is defined. But still, when I plot this, the argument of the eigenvectors there, this now becomes a mathematical prediction. What is the spatiotemporal dynamics that will result from the combination of this specific connectivity and these specific delays? So here we predict that there is a wave going, there is an offset going from here to there. And then when we go to the simulation in taking this experiment, there is no simulation whatsoever so far. It's just using our mathematical approach. But now I can test in the simulation, taking this connectivity and these delays, and then we can see that the simulations are actually confirming this mathematical prediction that we see there. And the point that I want to emphasize here is that there is no major fiber bundle projecting in this direction. Let me play this again. So this wave is actually emerging because of the sum of connectivity and delays. And now our approach is able to tell us, even before running the simulations, how these two things are combining to generate these specific spatial temporal patterns. And this can be applied even in these empirical cases. So I spent a lot of time to explain you the idea in the simplified case, just to build up the intuition. But all the intuition, all the ideas that I explained there, in the ring where everything is, it's easier to understand. Now we can go straight like to this empirical data and still have these predictions and still have like this spatial temporal impact of the eigenvectors and see exactly how connectivity and delays are combining to generate specific spatial temporal patterns, in this case, traveling waves. So I don't want to go too much over time. So just to summarize so far what I showed you, we have this new way to look at this nonlinear oscillator networks. And by using these operators and these functions, we found that there is this new link between the spectrum of this composite matrix and the dynamics. With that, we have this unified way to describe the impact of the network structure on the dynamics, and also allows us to predict what the dynamics will be even before running simulations, just based on the network structure. So now in the final part of my talk, I want to explore the question now, the second part of the question, I know that I set up for myself, but the second part of the question that I had is, okay, can we actually use the spatial temporal patterns for computation? So I will show you how we can actually use this mathematical framework to develop kind of like a theory of spatial temporal computations in these recurrent structures. So just very briefly, I just want to show you two examples before actually, very, very quickly, before I go like to the the theory of computation of these spatial temporal patterns. But I just want to show, to highlight here that using this mathematical approach, we're actually able, so for example here, we arrange these oscillators in a 2D sheet with these spatial distributed connections and delays. And we are able to show that the network organized like that is actually able to do short-term predictions of naturalistic scenes. So I will show you two examples of how we organize these oscillators in a 2D space with these distance-dependent connections, and how this will generate waves that will actually do computations. These examples, Lyle Miller in his talk already showed this here at the Wave Club. So if you're interested, you can go to the YouTube and watch his talk for more details here. But I just want to mention that, when we organize the networks like this, the network is actually able to perform computations with waves. So just very briefly here, the idea is that there will be a movie and frames of this movie, and we are feeding frames of this movie to this recurrent layer. So this input here will interact with the recurrent activity that is generated by, connectivity and delays. And based on that, so we'll have like complex spatial temporal patterns here. And based on that, the network is able to guess what is the next frame in this movie. And we do that in a recursive way that we call closed loop forecasting, that the output becomes the input for the next the next step. So very quickly, this is the ground truth. This is the video. This is the prediction that is coming from our approach. And the interesting thing that so it works. And the interesting thing that I want to mention is that in the recurrent layer here, that is the dynamics. We can see like kind of like these ghost legs and these ghost arms, which is like this complex spatial temporal patterns due to the interactions of input and recurrent activity. And we can actually show this is a combination, a sum of traveling waves going around like this organized network in this 2D space. And we can also do organizing the network like that. We can also do other like computer vision tasks, for example, image segmentation. So the idea is that we have like this data set with like two objects, binary, zero in the background, one in the object, for example. And we apply this as an input for the network. This will interact with the recurrent connectivity in the network, generate spatial temporal patterns, and based on that, we can do image segmentation. So here, for example, the input is here, the network is disorganized at first, the dynamics, but then quickly we can see the emergence of these traveling waves. And these traveling waves they are kind of like unique to the objects in the background. So they allows us to do segmentation in this dynamics based framework. So here is like a work that we can literally show the waves during computation. So as I said, Lyle Miller already explained this in more details in his talk, so you can go there. If you're interested, I just wanted to briefly mention these two examples to say that we can use now this framework to actually do computations with these traveling waves. And the last thing that in the last 5 minutes or so that I want to mention here is that actually using this framework, we were actually able to create like this this theory of spatial temporal computation in the recurrent networks with this organized spatial temporal patterns. So here, when you see CVNN, it means complex value neural network because we're using these complex valued oscillators here. And in this case, we have an input layer that is applying an input to the network. This will lead to the emergence, this evolution of spatial temporal patterns there. And then we have a decoder layer that is reading the dynamics of patches of this network. And then this decoder will be in the end, like we will binarize this and it will be like a pattern of zeros and ones that will change over time. And this will be our basis for computation. But this is all based on the dynamics that is happening here in the network. So long story short, again, I won't give you the mathematical details, we can discuss later, but we found that in this theory with our mathematical framework, we can write like from input to output, everything in a precise mathematical expression. So going from the initial state of the network, and the input is kind of like related to that, the input is kind of like kicking the network to specific places that we call this initial state. And then we can apply like this dynamics evolution given by that matrix explanation that I showed you before. So this will generate these two things interacting, will generate specific spatial temporal patterns. And then after that, the decoder is essentially reading the level of synchronization of each patch in the network. And then we apply a threshold function. If the synchronization is higher than that, is 1. If it's lower than that, is 0. And this will give us like this output decoder. And this is exactly precisely describing a mathematical expression. So just to give you an idea how this works, so this is similar videos as before. The colors here are representing the phase. So it is disorganized at first, so the dynamics is disorganized, but then we apply the input in the network, and mathematically we know that this part of the network will synchronize. So these detectors here, they will turn to 1. And using these patterns of zeros and ones, we can actually do the computation. And then after that, we apply a second input, and the network returns to this asynchronous states to this neutral state, so to say. So with that, just to show you a quick example what we can do here, we can actually implement logic gates. So we have X input, Y input, and decoder is Z, and this will be zeros and ones. And the idea is that using this dynamic space thing, we can actually complete the truth table. So if both X and Y's are 0, the network remains asynchronous and the detector will say it's 0. But when we apply either X or Y, we know that mathematically this will lead to the center of the network to be more coherent. So this will lead to this pattern here. Sorry, is there a question? I don't think so. Okay, great. And so the decoder will turn to 1. And the cool thing is that when we apply both things together, they actually cancel each other. No synchronization there, and the decoder turns to 0. So we can also do message encryption with this network. So the idea is that Bob wants to send Alice a message and use this network. And the idea is that everything is public. And when each part of the network synchronizes, this corresponds to one letter in the English alphabet. So they both have the network, and Bob wants to send this message. So he uses our mathematical approach to say, just apply these inputs at these times, and the letters will appear. And he sends this to Alice. And the key thing is that they agreed upon on like the secret key that is the natural frequency in the very first initial state. So because Alice has that, she runs the network, apply the inputs, and when she applies the inputs, clusters in this network will synchronize, and this corresponds specific letters. And then she decodes the message. Eve wants to eavesdrop to steal this message, so she has all the public structure, but she doesn't have the very initial states, the secret key and the natural frequency. So when she applies the ciphertext, she doesn't see the network synchronizing. So just to give you an idea how this works, Alice starts applying these inputs, and then parts of the network will synchronize. So here, and then the decoder automatically recognizes this spatiotemporal pattern, and then it recognizes the ladder. So Alice doesn't even know when the ladders will pop up. And the idea is that everything is defined by this mathematical approach. I think there is one more ladder. Yes, exactly. And then once it's done, and then the decoder says, that's the message. And the last example that I want to show you is that we can also do memory storing and updating because we have the mathematical expression. We can, say, I want to apply one input that will queue item number 2. So this part of the network will synchronize, and this decoder will turn to 1. But I say, actually, I want a number 6 to be stored in memory. So I can apply on the fly whenever I want because I have the mathematical expression, so I know exactly how to apply the input. And then the network will change from that part to this part here, and now this decoder will turn to 1. And it's all based, and then after the computation is done, it returns to the neutral state. And what is cool is that we actually create like kind of like a biohybrid version of this network, where instead of using this level of synchronization in the Heaviside function as the threshold, we actually applied like this state of the network as current to biological neurons using patch clamp. And then the spikes of these neurons become the decoder. Um, so for example, here we apply patches, the dynamics of patches of the network, and only when the patch is coherent will make the neuron actually fire. So here when we apply this patch in item number 2, the neuron will fire, but in item number 6, the neuron won't fire. And this is, we repeat this over different realizations, different neurons, different conditions, and this is fairly consistent. So we can, even though there are a bunch of nonlinearities in biological neurons, we can actually do that. And all of this is based on this spatial-temporal dynamics that is happening in the network, where we have this mathematical formalism to develop this theory there. So I don't want to go too much over time. So just to summarize the presentation and what I showed you here today. So, in the beginning, I set up like these two main questions. How is the structure of the network leading to specific spatial temporal dynamics? And then the second question was how we can use this for computation. So in the first part of my talk, essentially, I give you like this main idea of this mathematical approach. Using these operators and functions, we are able to introduce this new way to link the spectrum of this composite matrix with the resulting dynamics. And importantly, this is valid in individual cases. So with that, for example, we can predict traveling waves in our work with delays, and we can even do that in specific individual brain networks. And so based on this approach, we can now develop and train these neural networks to leverage these spatial temporal patterns to do computation. So we have like with this mathematics, like a theory of spatial temporal computations in these recurrent systems. And one thing that I didn't have time to talk here, but I just wanted to mention is that even though the applications that I showed you here in computations, they're fairly simple. I mean, I find them very interesting, but they're fairly simple. We just recently showed that there is these modern architectures in machine learning called state space models. They are kind of like an alternative to transformers. And we showed that there is a mathematical equivalence between these state space models and our model of complex valued oscillators. And so with this, we can actually show that waves going around the ring where the network is defined is actually a way to interpret the computations that these modern networks are doing. So if you're interested, this paper it's under review now, but it's already on the archive. So with that, I want to obviously thank you, my collaborators, all the funding agencies, and thank you for your attention. If you have any questions, happy to discuss now. Thank you.
Thank you so much, Roberto. It was very thought-provoking and gave me a lot of ideas that I think are exciting. This is great. Thank you so much.
Great. Thank you.
Let's open this up for questions. Um, why don't we begin with so the best thing would be if you have a question to type a summary of it into the chat, and then Uma and Irfan and I can sort out who's going to go when based on that as far as questions. But why don't we start with Bard, who why don't we start with Bard?
Yeah, I'm here. Great talk, Roberto. I have tons of questions, but I will keep it to a few of them. Okay.
Yes.
Just a few. Okay. In ring networks, for example, there's multiple stable states, and
Yes.
um, you made it seem like it would always go to the same state. You were predicting what state it would go to. Um,
Yes.
but in cases where there's multi-stability, um, how do you do that? Can you do that just
That
projecting the? Are you telling me you have a way to figure out the basin of attraction just from the initial conditions?
That is a great question, and I was hoping this question would come. Yeah, I didn't, and yes, I didn't go into details about the stability and the basins of attraction of this. The examples that I showed you here, so for example, in this ring case here, for this specific network, right? So in this
Yeah.
case, the network is it's monostable, right? With and without delays. So without delays, the synchronizing is the only
Oh,
stable
because
state
it's got
here.
such long distance,
Exactly.
and
Yes.
it
And
doesn't
with
fall
delays,
off with. Okay, so that's monostable. Okay,
but
that
yes, but that's about multi-stability. It's a great question. So we had a paper that it was published last year in PRE. I didn't show it here, but for example, say that you decrease the number of connections here, right? And then you're completely right. Multi-stability will appear. So from actually like this geometric interpretation of these eigenvalues and eigenvectors of this matrix K, we're actually able to predict the linear stability. Also, we are able, give me the connectivity and delays in this ring networks, and I'm able to tell you which states will be stable, and we are just finalizing a paper now that we're actually able to estimate the size of the basins of attractions based on this eigenvalues and eigenvectors of K. So this is a great question. The stability paper is already published. I didn't show you here. This example that I showed you here are monostable, but we are also able to handle the multi-stability case. And just now we are finishing a paper talking about the basins of attraction as well, which is a much more complicated problem. This
yeah.
basins can be, the geometry of these basins can be very, very complicated. But just using the spectrum of this matrix K, we are actually able to have a very, very good prediction and a very good estimate of the size of the basins and for each of in the case of multi-stability.
And since nobody else is asking, I don't see any more questions. Can you go back to the one where you had three examples of the ring? One went to synchrony, one went to
Yes,
the double wave, and then the
yes,
third one went to this really weird solution.
yes.
Is it the same network?
No, so the networks are different
Oh,
here in each
okay.
case.
It's
Yeah,
not the
yeah.
same network because
Now, so like this is essentially,
I
yes,
couldn't think
that's
of
it.
any ring networks which would give that kind of behavior.
So that's excellent question as well. So this is a network without delays, and without delays, the network transitions to synchrony, right? And then when we add the distance-dependent delays, the network goes to this wave state, right? So this is the same example that I used before. And this weird solution here in physics, this is called a chimera. Let me rephrase that. It's not a solution in this case. So because this is the transient state, right? So in this ring networks, when we have in this case we have a unique delays, one phase lag in the coupling, and the network has this very 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 long transients where part of
Oh,
the
so I'm
network will
watching a
synchronize
transient here.
exactly, and then but still like, and that's the cool part because we can deal with
Yeah,
multi-stability in the
yeah.
basins and like all these things, but we can also talk about transients here as well, right? So in the transients we are so like this eigenmodes here, they will be related to the eigenvalues of the matrix K. So given this geometric relationship between the eigenvalues of the matrix K, we are also able to predict how long the transients will be, and then we are able to predict when these weird states like these synchronized clusters will appear in terms of that. Because that's the interesting part, at least for me, because we have this physical interpretation. We know what these modes mean. We know like the relationship between these eigenvalues, what they will actually represent on the dynamics. And it can be, like in the solution of the system, like synchronizing and traveling waves, but also during the transient in this case here. So that's a great question.
And then last but not least, okay, in the last part of your talk, okay,
Yes.
those chimeras are generated by like the Strogatz-Abrams type network, right? In a ring.
It's similar to that. Is the complex, it's complex valued oscillator, so it's not exactly the Kuramoto model here, but it's related to that, and we have the equivalence in
And
Kuramoto.
so
Yes, so you're right.
in your secret communications thing or with the alpha,
Yes.
all you're doing is just moving those chimeras in different locations, right? And then decoding the regions that are stable. Is that, I mean, synchronized?
Exactly. And the key point is because we have this analytical solution, we know everything deterministically ahead of time. So Bob knows all of this ahead of time. Alice doesn't even need to know when these clusters will appear.
Okay.
And then Eve, because Eve doesn't have the very first initial condition and the system is deterministic, and actually these chimeras have been shown to be chaotic transients. So, deterministically speaking, and we tested this numerically, if you try like say, because Eve has everything, the network, the encryption, the decoder, the ciphertext, but she doesn't have the natural frequency and the initial condition. So we tested like, thousands of combinations, say that Eve doesn't have that, so she needs to guess. And because the system is deterministic and these transients, they actually have positive MLE, she never has these chimeras like appearing. So she's not able to actually get any word there. So this is kind of like a good thing about being deterministic in this sense, and like with this chaotic transients. Yeah.
All right. I'll save any follow-ups. I'll email you.
Yeah. Yes. Thank you. No, great question. Thank you so much. I was hoping that the multi-stability question would come. Thank you.
Oh, here, Lyle is saying something.
Hey, Lyle, welcome.
Hi, yeah, just a quick technical point going towards Bard's question about the initial conditions. I think it connects with what you're saying because the and earlier Roberto showed the eigenexpansion under the nonlinear operator. And I think the key detail there is that you can account for the initial conditions while you're eigenexpanding under the nonlinear operator, and you have this small var sigma. So even if the one of the eigenvalues is large, if you're very, very close to one of the eigenvectors there, you can go towards that, even if the eigenvalue for lambda 2, for example, is smaller in real part than lambda 1. And so this is like it's a different way of looking at the system. It's that we're not, kind of linearizing around a fixed point and then predicting long-term dynamics from that. We're actually able to account for the linear and nonlinear operations in the system in this operator framework. So it's a slightly different way of looking at the nonlinear systems, but I just wanted to mention that technical point.
It appears since that K just contains everything, you could have omega I as well. It doesn't have to be all the same omega, or does it?
That is correct. Great point. Yeah.
And that's actually how we do the image segmentation.
Ah,
Yep.
Very cool. Are there any other questions?
I have two. I can keep it short if others are not asking. Great
ahead.
talk, Roberto.
Thank
The
you.
first one is related to the part that you use the connectivity. How did you calculate the delays for that human connectome thing?
Oh, great question. So here, from this fiber, so we have like two things, essentially the number of fibers that are connecting different regions. And by counting the number of fibers, we can estimate the weight in that connection. And then we have the physical distance of these fibers, right? So from DTI, we can actually also have this distance as well. And then there is the assumption that the conduction speed is fixed. It doesn't need to be, we just started there, right? So fixed conduction speed, and then we have the distance, and then we just divide, and then we have this distance-dependent delays.
Right.
But like that's one of the things that is interesting, right? Say that you want to test what happens if we have like different myelination, different patterns, and like all this things. So fixed like in the same conduction speed is obviously an approximation there, right? But you can change that. This will in turn change this delay matrix. This will change the K matrix, and as Bart was saying, everything is there, right? And then we can calculate the eigenvalues and eigenvectors and see how that is actually changing the patterns. Yeah.
I see.
Great question.
And related to the last part, and probably there's something I didn't understand, but how would it be different from these echo state machine literatures? That if you have enough richness of dynamic in it, the recurrent.
That's a great point. So you said echo state networks, right?
Yep.
So yeah. So, and this application here is literally a reservoir network. So we are only like we are keeping everything fixed here, and then we are training these output weights, right? So this is a reservoir type of network, but the key thing here is that we have the mathematical understanding how the connections are interfering with the recurrent dynamics here, right? So in the traditional way of doing reservoir, you do everything like random inside of the reservoir, right? So the idea is that you're sending everything to a very high dimensional space, everything is random there, and then you make sense of that, and then you're able to predict like chaotic time series, for example. But here we structure this with this distance dependent rules like connectivity and delays, because we know from the mathematical approach, we know this will generate these waves and like all these things. And then so like it's kind of like it is reservoir, but there is using these specific insights that are coming from like this link between network structure and the waves that are appearing there to do this kind of like dynamics-based computation.
Thanks, Irfan. I think this is really thought-provoking, this prediction.
Yeah, no, thank you so much.
Oh, look, and Lyle just put a link to the code in the chat. Thanks, Lyle.
Oh yeah, we have the code is great. Take a look there. And if you have any questions, like feel free like to reach out by email to Lyle or to me, and happy to discuss this for sure.
Yeah, it sounds great. Thank you.
Awesome.
Any other questions? Okay. Roberto, that was a very it was super thought-provoking, and it was a wonderful distraction from the heat. So thank you so much for both of those
Yeah,
things.
yeah, I'm glad that I could help with that. Thank you so
Yeah.
much. Thanks for having me here, and
All
happy
right.
to discuss at any point.
It sounds great. Let's be in touch. Have a great day.
Awesome. Have a
Take
good
care,
one.
everybody. Thank you.